It's a pleasure to be here, and as Jay said, I'm going to be talking about the geotechnical aspects of these more recent earthquakes. David introduced a number of different earthquakes, but I'm going to focus in on two in particular. The two I wanted to focus in on are the 2011 Tohoku earthquake and the 2010-11 Canterbury sequence that affected Christchurch. And the reason I wanted to focus on these two is because I believe these two are going to be seminal events in a lot of the different things that we do in geotechnical engineering. It's similar to when you think back to the 1995 earthquake that affected Kobe. That event really changed a lot of the things that we do when we look at pile foundations and liquefaction. And it's just kind of really changed things. And I think these two earthquakes are going to have similar effects. And they're going to have similar effects for a couple of reasons. Number one is, as David pointed out, these are extremely well-recorded events. So we're going to know the motions. It affected a widespread area, so we get a set of data and a quantity of data that's just kind of unprecedented. And it's really going to be a great learning opportunity. Some of these lessons are going to come pretty quickly, quick observations. And then some of them take a little while longer as you need to go back out and collect some more detailed site data and other information. And then some are going to take a few years to kind of milk out as we go through more detailed analysis of some of these. So what I'm going to try and do through this talk is kind of flag some of the quick lessons as well as flag those areas where I think you'll see changes coming out over the next couple of years as we study these data. So that's the plan for today. What I'm going to do is go through this as I picked just a kind of a subset of topics that we can go over. I wanted to start by talking about the kind of the pervasiveness of the liquefaction damages and just how that reinforces some lessons that we've learned before, but they bear repeating. Then I want to take a look at the effects of liquefaction on ground deformations and then on building foundations. I'll show you a little bit about the foundation repair techniques being used in these two affected areas. We'll look at utilities, levees, and dams. I'm going to focus in on one dam in particular, and then we'll wrap up with some concluding remarks. What I'll try to do as we go along, if you have any questions, Don, just wave your hand and we'll just pause and answer them as we go along. So that's the plan. Okay, so let's start with just the general fact that both of these events had really pervasive damage to liquefaction. And I think the stepping back, the key thing about this is that it was known and or identifiable hazards. There really wasn't a lot of surprise about the extensiveness of the damage. And so, for example, if you take a look in Japan, a lot of the liquefaction that we're studying is towards the southern area of the affected regions. For a number of reasons, in part, differences in geology from the north to the south, and of course to the north, a lot of the liquefaction along the coast is then obscured by tsunami effects, etc. So, in the affected regions, you see that we have the Tone River region out here. There's a lot of recent sediments as well as some reclaimed land we'll look at. And then along the margins of Tokyo Bay, a lot of reclaimed land there. I'm going to take a look at two areas just as examples. One is the city of Ueresu in Tokyo Bay, and then the other one will be Kamisu up along the Tone River. So if we look at Ueresu to start, this is a reclaimed land, and natural shoreline is right along here, and then it was reclaimed in a series of 6 different cells. Tokyo Disneyland is located over here. It was on improved ground, performed quite well, but the majority of the reclaimed land was not treated. And a lot of this area was constructed using techniques you recognize, hydraulic filling and barge dumping, which we know produces very loose materials. And then when those materials liquefy during an earthquake, you get very dramatic settlements, a lot of ejecta to the surface, and very extensive damage to this very well-developed area. There was no surprise to this. Everyone in the affected areas knew they were on reclaimed land. They knew they had a liquefaction hazard. Many of the homeowners understood the risks in their neighborhoods. The truth is you kind of get numb to some of this. And what happens is you've heard the word, you know it can happen, but you didn't understand the severity or the pervasiveness or what it means when your entire city is affected. And so I think there's a lesson about that we'll come back to later. Now, on kind of a smaller scale, this is an example up from Kamisu City. This is some work by Tsukamoto and Kokushu and colleagues in Japan. And this is just one of many examples. Whereas if you drove across these different cities, you could go through these areas and you would find neighborhoods where there is no evidence of ground deformation, settlements, or ejecta. And then you'd come into a neighborhood where the damage was pretty severe. Broken utilities, settled houses, street disruptions, etc. And it would be very concentrated. And it turns out that most of these, again, were very identifiable, localized problems. This is an example where Tsukamoto mapped what were historical areas of swamps, rice paddies, and then gravel pits. They had been mining the gravels and then backfilling the old gravel pits with loose materials. And you could pretty much map up the areas of liquefaction and lateral spreading with those old features. So these are reclaimed rice paddy fields, swamp fields, and then the areas of liquefaction, largely lining up with what could have been identified strictly off of old historical photographs and or maps for the local region. So I think both of these just really emphasize a lesson we already know, that the first and most important things to do is make sure you understand your local geology or your local historical records before we necessarily have to jump into drilling and borings and crunching numbers. Christchurch is very similar in the sense that very well-known liquefaction hazards here. You have the city and surrounding areas founded on alluvial outwash plains. We know the river snaking through the city. We know we have young recent sediments, fills in certain areas. We know these materials are going to be younger and more prone to liquefaction. The conditions here are a little bit more heterogeneous. Being natural deposits, properties can change over short distances, but in general you know that you're going to have lots of younger recent sediments throughout the area that are prone to liquefaction. And most everyone understood that and just maybe didn't recognize how pervasive it could be in the event of the level of shaking that they in fact experienced. And this map just shows just how widespread it was. The red zones are the moderate to severe liquefaction as mapped by Misko Kubernovsky and his colleagues at Christchurch. This photograph is just an overview of one neighborhood in the affected area. You can see the river in the front, and then that entire neighborhood, you can just see the water, all the ejecta on the street surfaces, widespread damage. Right? Kind of keeping in mind, we'll come back to this again later, but it's not just your one house that you need to think about, but you need to think about the entire neighborhood or city. Question?
Yeah, if T equals 0 is the beginning of shaking, is it known when the liquefaction occurred, whether it was during the shaking, after the shaking, or how many minutes of the 6 minutes before it began?
Yeah, I haven't really seen anything where that's been really digested. There are certainly strong motion records where you can look at in certain spots where it would trigger, but you also know that the severity of movement varies from areas with more than a couple meters of movement to areas where it's just a few inches. And just based on that alone, we can expect that when it was really loose, it probably triggered very early in shaking. And then when it was moderate movements, like a few inches, more likely it would have triggered sometime during shaking, possibly even towards the end. I think in terms of the people's descriptions, it's fairly variable. So I don't think there's one answer. I think it just represents the variability of the geology. Okay, so again, very, very pervasive hazards. Now what this means, of course, is that lots of infrastructure is affected, and we know the motions. We see lots of things are damaged, from utilities to houses to bridges, etc. And so again, we're going to have a quantity of data that we've never had before. This was just one other example illustrating the role of understanding your local geology. This comes from Watherspoon. This is an area in near Christchurch. This green oval here is the outline of a very large lateral spread which affected this neighborhood in here. And the red line mapping along through here is the bounds of an abandoned river channel. And not surprising, if you've had a recent river channel, the sediments backfilled in that channel are going to be the younger, more recent materials, generally more prone to liquefaction. And in fact, you could have mapped the bounds of that lateral spread from understanding the historical variations in the river channel. So again, kind of emphasizes something that sometimes is forgotten in practice, to make sure that you have that geology and the historical records first as part of understanding what you're going to expect at your site. So that kind of gives you just a sense of the nature of the hazard. Now I want to zoom in and start talking about what it means for ground movements and the performance of buildings. So let's start with Uaresu in Japan. This city was very well developed. There's a large number of fairly tall buildings which are founded on pile foundations. Those piles are fairly well designed. They go down well below the liquefiable settlements. Buildings show no evidence of settlement or any problems. And so they provide the strain gauge against which we can measure settlements of the surrounding ground surfaces. So as you walk across the city, you can look at these different buildings on pile foundations. You could walk through areas where there would be no visible settlement adjacent to the buildings, go to a little further down the street, maybe pick up 4 or 5 inches, and then come into areas where maybe you see a foot, and you could go to areas where it'd be a little bit more than that, a little less, and it varied as you walked across the city. And so you have a lot of different cases that we can start to look at. Now, that's the buildings on pile foundations. For comparison, we can start to look at the buildings that are on mat foundations or shallow foundations. And this is one really nice example. Building on the left is on piles. You can see the ground surface is settled maybe about a foot relative to the building. If you look just to the right of that is a 3-story building. This building's on a mat foundation. And you can see that the building is climbed leaning backwards, and it's settled into the ground by an amount that's probably about another foot or so. And so if you think back to what's a pretty common assumption in practice, well, it's pretty common to assume if you want to estimate the settlement of a building is we take our borings and we estimate potential settlements using charts which implicitly assume that the settlement is due to reconsolidation of a liquefied sand. That means that we're assuming that the settlement is only due to the water being expelled from the sand and the sand consolidating. We then assume that a building on a mat foundation would follow the ground surface and settle a comparable amount. Many of these examples, just like this one, illustrate that right there you'd be off by about a factor of 2 in terms of what the building would do. Now, part of that is going to be affected by how thick of a crust or non-liquefied layer you have over top of any of the liquefying sediments. Here, the crust is probably on the order of about 3 to 4 meters, and the building's not very heavy, and yet you can still see that it settles substantially more than the surrounding ground surface. So I think that's a very good reminder. You also see in this picture these sandbags here where they've been collecting the ejecta that's filled up the streets and covered sidewalks, etc. And that's a reminder of one of the mechanisms that leads to settlement is the loss of ground. When we get these events that produce a lot of surface ejecta, that sand that's coming out of the ground and being eroded to the surface is adding to the settlement that the buildings are experiencing. That's not included in the current design methods that we use to calculate settlements. I think just goes to the humility of we're trying to use these methods as a proxy to estimate the nature and order of the damage, but we're not necessarily getting all the details in how that settlement occurs. So that's just one example. And if you go across the city, you don't have 1, you don't have 10, you've got literally dozens, if not hundreds of cases that are ripe for compiling into databases and then starting to evaluate our engineering procedures. Not to see if we can predict one case, but to see if we can predict dozens of cases. It's a great chance for us to understand if we have bias or just what's the nature of the dispersion in our predictions. This is exactly what Professor Tokumatsu and his group have been doing. This is some work with Katsumoto, where if you go across the city of Uaresu, the red areas here are where you have severe liquefaction, settlements say on the order of a foot or so, and then you have green is more moderate, yellow is slight. I got that backwards. But either way, then the white is areas where there's very little or no visible settlements. And you go across and you compile SPT boring data that came from the design of the various buildings, and that's shown in the graphs along the bottom. And you compile that data, and then you can see how well would you have predicted the settlements across the city. This is the results of some of their initial analyses. And in this pair of graphs. What's being shown on the x-axis is the range of observed subsidence or ground surface settlements. You can see observed settlements ranging from 0 to maybe on the order of 30 centimeters, or about a foot. And then on the y-axis are the estimated settlements. And these are computed using the Architectural Institute of Japan procedures, which follow the procedures that Professor Tokumatsu published in Soils and Foundations in the 98 special issue after the Kobe earthquake, and which are very similar to those that we would use in U.S. practice. The curves shift a bit, but the forms are all the same, and so the general patterns, the conclusions would be the same. And what you see is they're at least consistent in the sense that you predict settlements from 0 to 30 centimeters and you observe 0 to 30. The challenge is that there's a fair amount of dispersion in that prediction. Now, on average, doesn't look like there's any strong bias, so that's good. But that dispersion should give us a little bit of pause into just how well we're predicting settlements. In this particular case, there's, I think, a couple of things going on. One is that these are fairly brittle sites. You have a fairly loose material. Ground motions across Urayasu were pretty well recorded. There's about 17 stations of recordings in Urayasu alone. They show ground motions varying from about 0.16 to 0.24 Gs. If you get just a little bit less shaking than is required to trigger liquefaction, you don't get much settlement. If you get a little bit stronger shaking and you trigger liquefaction, very quickly you're getting 10 or 20 centimeters. And so it's a very brittle system such that it's going to be very sensitive to the ability to predict these small variations in ground motions. More importantly, you can use these analyses to understand that if it had been shaken at 0.1 G, you don't get much movement. At 0.2, you're starting to pick it up. And if you'd shaken it with 0.3 or more, you'd expect even larger settlements. So you're going to take them in that kind of context. Okay, but what we also are curious about is there anything else going on? Is there some other reason why settlements, sometimes we predict 0, but we observe 20 centimeters. Sometimes we predict 20 and we observe very small settlements. And we wanted to see if there's something else we could discern from that. So we partnered with Professors Ishihara and Tokumatsu and their colleagues in going out and doing surface wave profiling at a number of sites. This was an effort through the Geotechnical Extreme Events Reconnaissance Association, or GEER. This was a team. I was the lead with Professor Nick Sitar, and then Professor Brady Cox, shown over here. He had another NSF Rapid Award, and our two groups were very closely cooperating. There was about 20 individuals that were involved in this group, so a lot of contributions. And what we did is we went across the area of Urayasu, doing tests at different locations. These stars show we did surface wave testing in areas of the native or natural alluvial materials, some of the older reclaimed lands, and then some of the most recent, younger reclaimed lands, phases 1 and 2. Those different sites are also sprinkled around locations where we had severe liquefaction effects to essentially no observable deformations. And we take all those data and then we bin them and sort them and try to see if we can pick out any patterns at all. The punchline is that we didn't really see any significant differences arising from anything we could correlate with shear wave velocities. So that's shown in these three graphs. The graph is shear wave velocity corrected for overburden stress, VS1 values, versus depth. The young alluvium and the fills are, say, mostly in the upper 10 meters. So let's focus up here. Starting at the left, the green line is the average shear wave velocity profile for all the stations in native soils, native alluvium, that we looked at. The blue line is the average for all the youngest phase 1 fills, and the red line is the average for all the older phase 2 fills. And you can see that there's no discernible difference between those three average results. And you can take those differences in context. The graph on the right, there's 4 red lines here. Those are 4 different individual sites where we had severe liquefaction. The 3 black lines are 3 individual sites where we had no ground movements or boils. And you can see just the variability between individual sites is much greater than any of the small differences that we see on average. The middle graph is just re-bitting it a little bit differently. It's looking at, red line is the extensive liquefaction areas, and the green line is the no ground failure areas. Again, nothing we could do to bin these showed the shear wave velocity was going to help us discern where we did or didn't get liquefaction. That kind of just reinforces where a number of us have been kind of going over the last few years about not having a lot of confidence in shear wave velocity as a really fine predictor of liquefaction effects. That doesn't mean it's not a useful tool. You can certainly get into sites where a very high velocity, much higher than you expect, is telling you something. It's telling you about cementation or other effects that can be an important consideration. But when you're looking at these young materials, it really wasn't picking out any of the differences. Okay, so that's our surface wave testing. Another aspect that we spent a lot of time looking at were the strong ground motion recording stations. We compiled a list. There were about 22 stations where strong motion recordings were obtained on sites that showed evidence of liquefaction. And we have about 16 sites where no liquefaction was observed, but the recording stations are on sediments that you would have expected to liquefy. So we have a nice data set that we can start to look at in a lot more detail, in part because you have the recordings. You know the ground motions, and you can understand exactly what the demands were at those sites. I'm not going to go through all those stations. I picked out 3 that I wanted to go to and just illustrate some points. These 2 stations are pretty close together. They're in Chiba, which is also along the margins of Tokyo Bay. Station on the left, there's no evidence of ground surface settlements or ejecta. There's some tall buildings around here, no evidence in the immediate vicinity of this station. And you look at the acceleration records right beneath it. There's no characteristic change in the acceleration records that would suggest liquefaction happened. In comparison, the station over here on the right, there's a power-supported building just out of this photo. Settlements were about almost a foot relative to that building. You see extensive ejecta out on the ground surface, and then the recording station right there in the background. And in fact, you can see in the strong motion recording a very strong change in the nature of the ground motions, maybe about midway through shaking, and it includes some of those strong acceleration spikes that David mentioned earlier that we associate with the effects of the cyclic mobility behavior of the sand as you soften, and then periodically stiffen and regain strength as the strains build up. Right? So we've seen this now in physical models in a number of different earthquakes. It's a very good example of why you have to be careful with site response programs that do monotonically softening stress strain behavior, and you can damp out that kind of response. So I think these are going to be a great illustration and chance for us to evaluate our site response programs. And I think it'll reinforce some of the lessons that a number of us have been saying for a while. So at those 2 stations, we can also take up the boring logs. These are the logs that come from the KNET websites, so you can go and look at them yourselves. On the left is, again, the station where we had no observed ground settlements. This is the site which had about a foot of settlement. We've got a question?
Does that last slide mean that it didn't liquefy until 2 minutes into the shaking?
Yes, I think so. That's how I would interpret it. There are some more detailed techniques. That was very obvious to the eye. But there are some techniques where what you can do is you can take the recording and you can start to kind of break out the frequency content characteristic over time, like wavelet analyses, and then it's a little clearer, it's certainly fancier, shows the elongation of the site characteristics. And you have to be a little bit careful because of the incoming motion can change. But if you get to a kicknet site where you have the downhole recording, well then those are great, because then you can see the transfer function basically softening. But yeah, I think that one's pretty clear. Okay, so taking a look at these 2 boring log profiles, start over here on the left. You've got a sandy soil from about 3 meters to 10 meter depth, and it's overlain by silt. One of the first things you learn is that the characterization of these sites doesn't include the details we would like for our standard liquefaction assessments. So for example, there are no Atterberg limits for the silt layer. Now what we can do is we can take that silt. If you thought that silt was non-plastic you would predict with those low boil counts that this stuff would have all liquefied in this earthquake. However, if you look at some of the other geology around the margins of the bay, you would expect that that silt is actually quite plastic. And if you treat it as being slightly plastic, and we estimate undrained strengths from the CPT data and other data in the area, you would show that even with a very modest amount of overconsolidation, this plastic silt would have enough undrained strength that you would not expect any cyclic softening during an earthquake. That would be consistent with the absence of any movement at the site. We just need some Atterberg limits to kind of confirm that extrapolation in the geology. In terms of the sandy soil, we don't have any fines content. So based on typical visual descriptions, you might expect it's around 20 or 25%. If you do that and you take the blow counts, which are on the order of 20, and you calculate the cyclic resistance ratios, these are using the procedures that Idris and I have proposed, and the site was shaken with about 0.18 Gs, you would get by and large that you would expect to not get liquefaction in that layer, and even if you thought that one last blow count meant anything, it would mean it would be a thin layer and it might not be enough to cause much of a consequence at the surface. Certainly, what you need is some fines content data and some gradations, whatnot, to be able to make sure that those details of the analysis are supported. That's what we need to get to. And the station on the right is perhaps a little bit easier. Blow counts are now on the order of 15 to 20. And you have a fairly clean sand all the way down to 20 meters, and the site is shaken a little bit more strongly, about 0.24 Gs. So you've got cleaner, looser sands shaken more strongly. You get liquefaction throughout the depth, and you see about a foot of settlement at the ground surface. So the results are pretty consistent with what you'd expect. So those two are kind of, that looks pretty reasonable. This station is an example where things don't work quite as well. This is a site which is near Uaresu. It's in the native soils along the shoreline. And you can see no signs of settlement or boils at the state recording station. There's buildings on piles nearby. No evidence of ground movement there. Strong motion record shows no evidence of softening in the acceleration records. And if you go over and look at the boring logs, what you have is maybe a meter or so of sand, maybe another couple meters or so of sandy soil, maybe expected to be silty sands, but again, no gradation data. And then over that silt layer, which again, if it's plastic enough, you would not expect any problems with it based on the level of shaking. The site was only shaken about 0.16 Gs. Nonetheless, if you take these blow counts, which are on the order of about 10, you would expect that you might have had liquefaction occur at that site. That would be inconsistent with what you observe at the ground surface. And so there's a number of things that you would want to take a look at to see what this site's telling us. A couple of those are, number one, these sites now need to be characterized in a little more detail. We are missing fines content data and any indication of the plasticity of those fines. So that would help sort out a little bit. And then the second thing is that if you look in the details of the analysis, you can swing those points from one side of the CSR line to the other side with two factors. One of them is the magnitude scaling factor, and the other one is the estimation of the CSR, in this case, the R sub D factor. And what you get is that in both cases, those correlations, those relationships were developed using records for magnitudes upper 7, 7, 6, 7, 8, and less. As David showed, we didn't have a lot of data out to these very large magnitudes, and those magnitude scaling factors and R sub D factors were never developed for a magnitude 9 earthquake. And what it appears to be is that those relationships, when extrapolated to magnitude 9, are slightly conservative. And I think what you're going to see is we can now take these records and revise the magnitude scaling factors and R sub D factors, and I think that would in part contribute to the differences. And again, so that's 3 out of 38 sites that are just primed for looking at. We also did some cone penetration testing at a number of sites in Uaresu where we have strong motion recordings. These are private sites, gas company sites, where the recordings again range from 0.16 to maybe 0.24 Gs. These are just 2 of the different sites where we have CPT data, standard cone tip resistance and friction ratio versus depth. Soil behavior type is color-coded, and then your cyclic resistance ratio versus CSR. This site on the left is a site with no observed ground movement. Site on the right, more moderate ground movements, several inches of settlements. And when you take a look at these two, they illustrate kind of the same kinds of lessons. We, again, have no fines content or plasticity data to check the CPT method, so we need that data. Both of these analyses are shown going point-by-point analysis, which is something just to illustrate some of the problems you can have with that, and it's something you need to take a look at after you've done the analysis. So for example, first of all, the silt, if you treat that as being an undrained strength, you would show that it's safe against cyclic softening, so it's not a problem, because it's only about 0.18 Gs of shaking. And then in terms of this sandier layer right in here, tip resistance is on the order of 10 MPa, or a little bit better, and you can see that you're kind of slightly better on average than a factor of safety 1, but you certainly start to get some lower factors of safety down here in these thin interlayers of finer grained materials and sands, and you get lower factors of safety in this upper part of the CPT trace where it looks like you have an upward fining sequence. If you thought that these two zones were going to contribute to settlements, you would predict a modest amount of settlement, but it would be inconsistent with the observations. Both of those cases, I think it goes to the same list. We need some fines contents, we need some characterization of those fines, the Atterberg limits. Magnitude scaling factors and R sub D would play a role in both of these, and then as well looking at the influence of these thin layer corrections. So I think that's a good example of some of the things you need to look out for. And over on this site, it's a little clearer. What you see now in the sandier zones, tip resistances are less, maybe on the order of 5 to 10 MPa. So you have looser sands. You also have a stronger shaking, about 0.21 Gs. So looser sands, stronger shaking, you get liquefaction, and that's consistent with the observations. These data and the SASW data should be on our GEAR website sometime before Christmas. It's a great data set for anyone interested in digging into it. It's there for everyone to use. Okay, so that was some examples of just looking at ground movements. I want to switch and look at some of the building performance. Throughout the city of Uruguay, you had a lot of residential homes affected by liquefaction, literally several thousand. I'll give you some statistics later. This is just one example. You can see the building is tipping backwards, perhaps a degree and a half. And there's a watermark on the side of the building. You can see that there is a lot of surface ejecta. Again, the building has settled. It's a very light building, and yet it's settled more than the surrounding ground surface. The building itself, doors open fine, windows work fine. Talk to the occupants. There's no structural damage to the building itself. So the buildings did okay. And this is another example from Kimisu. You see both of these buildings, very dramatic tips. You see all the ejecta in the free field. Again, doors, windows, the building themselves are structurally fine. And the reason they're fine is they're on really good foundations. This is a very common type of construction in the area. Turns out to be about an 8-inch thick reinforced concrete slab with these reinforced concrete beams around it. This makes a very stiff box, which is able to withstand differential settlements and tipping without causing distortion into the structure that's bolted to it. And so that's why the structures themselves appear to do well. Now all your utilities are gone. Some of these homes are very uncomfortable to live in. In fact, many people get a motion sickness if you live in a building that's tipping more than a degree. So a lot of them are not habitable, but they can be repaired. And I'll show you some of that in a bit. Just to contrast that with the performance of foundations in the Christchurch area, just a residential neighborhood. Again, you see all the ejecta coming to the surface, contributing to settlements. The ground movements, a variety of different forms affecting the buildings. Here's an area of lateral spreading where you see the structures essentially stretched, and the stretching causing large cracks to form in what is essentially just a simple slab-on-grade foundation. And so this home is essentially destroyed. And that's because one of the two more common foundation types in this area is a simple slab-on-grade foundation. There's not a lot of reinforcement in the slab that's going to be put down here. They just are not strong enough to resist any ground deformations. And so you are very vulnerable to ground movements. Now, Misko Kubernovsky and his colleagues have documented a lot of the different damage patterns, and you get a little bit of everything. You get tilting, hogging, stretching, sagging. It really kind of depends on what the ground surface does. In all cases, the two types of foundations, the concrete slab as well as these timber floors, just can't resist the movements, and the structures suffer quite badly. Nearly 20,000 residential homes were damaged by liquefaction alone, and over 6,000 of them were damaged beyond economical repair. So just a huge impact on the city. This is a real challenge for the whole city and area to recover from. I'm going to show you a pair of maps that describe efforts to categorize and recover. Laurie Johnson is later going to talk about these maps, kind of the political process, insurance implications, recovery implications, etc., later this afternoon. Just to kind of introduce them, these are maps that come from the Canterbury Earthquake Recovery Authority. The CEERA organization was charged with first breaking areas into red zones and green zones. The red zones, shown here in red, are areas where recovery would be very uneconomical, in part because of damage to the homes, in part because subsidence makes it very prone to flooding, in part because of damage to the utilities, the levees, and everything else, such that bringing those neighborhoods back was considered uneconomical. Everything else was a green zone that you had a potential to go, and that was then handed off to the Department of Building and Housing to develop technical categories, and those are shown in three different colors here. Technical category 1 is where liquefaction effects are expected to be modest, if any. Technical category 2 would be more modest, moderate liquefaction effects, something say on the order of a few inches. And then technical category 3 is where you expect more significant liquefaction effects, settlements, movements on the order of several inches and much larger. So that gets into the realm of much more difficult to recover from. Just zooming in, you can see that these the red zones and technical categories 1 and 2 cover very large areas. Huge portion of the developed areas and neighborhoods are affected by it. Just to kind of remind you again, CEERA set the red-green zones, and then Department of Building and Housing set the technical category maps. The Earthquake Commission assesses the land and property damages, and they would handle the repairs for the damages in the 10 to 100,000 range, which was kind of, everyone was insured to that. Anything above 100,000, you were in private insurance hands, in which case you were handed off, if you had that insurance, to them. Within the red zone, there was a program of the Crown to buy back the properties. You can go to the CEERA and Department of Building and Housing websites. They have great records and documentation of what's going on. I encourage you to look at those. You can also go to the Earthquake Commission and look at videotapes of all the hearings and testimony of people. So there's a lot of other lessons, kick back in the evening, load up YouTube, and you're good to go. In the red zone, as of October 2012, more than 6,000 of the almost 8,000 property owners in the red zone had agreed to sell their property to the Crown. The first almost 5,000 of those settlements cost almost $1 billion, or about $200,000 per home. So it's a huge hit on the economy. Earthquake Commission is currently leading a drilling program throughout technical category 3 zones to try to build up a common database so everything can be shared across everyone who's affected. And and that is ongoing. That takes a lot of time, right? We're a long time past the earthquakes and still collecting data on guidance on how owners can recover or rebuild. Another interesting point is just that the changes in the geotechnical practices that come with this. There's certainly been an influx and a second guessing of all the procedures of how you drill holes, how you take care of your CPTs, how often you take samples, how often you do lab tests, etc. And so you do see a lot of discussion and changing in common practices in response to this. So that was some idea of just how extensive the damage was.
How were they doing the buyouts? Is it voluntary or?
Okay, so I'm going to let Lori Johnson do some of the political issues, but my understanding is you don't really have a choice. And part of it is because you're not going to, she will give an example later of, a homeowner who had a well-built foundation, kind of had done things right, but your problems are now you're stuck in an area that you're not necessarily going to have the flood protection, you're not going to have the utilities, you're not going to have the other things. And so it raises a lot of issues about who are the winners and losers in these red zone areas. And then the political decisions of how one sets the boundaries is you have a sharp binary switch from one side of the street to the other. But I don't think you have a lot of choice. Maury? Yeah. So in terms of some general lessons, so certainly I think Maury's question is about lateral spreading, and I really didn't pull out many numbers and examples of that. I was focused on settlements. There are equal number of great examples about lateral spreading. If I was to draw out a couple things that were real good examples for quick lessons, one of them, I think, comes out of New Zealand, or some great examples. One of the things in our standard practice is you take an empirical data for how lateral spreading displacements vary, say, from a river channel with distance from the face. And if you take a bunch of empirical data, you see that displacements generally get less as you get further away from the shoreline or waterfront or riverfront. And so you can put a curve through that, and you can therefore say settlements or lateral spreading decreases with distance from the face. There's some great examples on large lateral spreads where that might be true on average, but there's great examples of lateral spreads where the whole area going back 50, 100 meters spreads uniformly. And so the displacement 100 meters back is the same as 5 meters back. So it moves largely like a block. And then there's other cases where it's much more dramatic the other way. So it's a bit of a binary process. And I think those give some good examples of where we have to be cautious using distance from a face as an argument for arguing that lateral spreading is not going to affect us so badly. So I think that's one where you'll see some changes. Everything else I saw was pretty predictable. There are some great examples of lateral spreads in the urban areas that were along old infills, old channels, some of the old canals that had been infilled. So again, knowing the historical construction pretty much identified those. And I think there's one other thing that's interesting about it. In like cities of Uaresu, there's some examples that Professor Tokumatsu is looking at that show the effects of the dynamic lurch. So even without permanent lateral spreading, just the lurch that comes when the soils liquefy, that cyclic displacement has caused some damage to some different types of foundations. And I think those will be some that are of interest. Everything else kind of reinforces what we've seen before. Does that make sense? There's maybe one more. Yeah. Sure. Yep. Okay, I missed the first part of what you said. Could you say? Oh, for bridge foundations. We didn't see a lot of problems with liquefaction. The bridges in Japan. There are some examples of settlement at approach embankments and things like that, but nothing like really dramatic. In New Zealand, there are a number of really good cases where what you're seeing is the embankments spreading towards the channel, and certainly some damage to the underlying pile foundations at those abutments. And so there's a number of cases that Kubernovsky and others have documented that I think will be really great examples.
Is there any plan with this idea of geotechnical learning to do anything with the red zones to try to recoup the money that's spent to buy the house? Are you going to try and use this land, or is it just going to sit?
You know, I don't.
Thought that through yet.
Yeah, no. That whole process is still ongoing. I think you're going to find Lori's going to talk through that quite a bit. The whole process of what is red and what's green is very subjective, very difficult, right at those margins. And I don't believe there are concrete plans for exactly what's going to happen in the red zone at this point. But Lori, she stepped out. But she'll talk a bit about that later. Daniel? Or?
You mentioned about this, insurance is going to cover the cost over 100,000.
Yeah.
And those for the home already have insurance, or is government negotiating this insurance?
Well, Bill, my understanding is that everyone's covered by the government insurance, right? To $100,000, and once you go over $100,000, then you have to have private insurance. Yeah.
And $100,000 a year costs you a grand total of $56.
Yeah.
You showed a CPT profile with the CSR and CRR, and the one you said something about the thin layer correction, and I'm just wondering if that had been applied.
Yeah.
Right there, one on the left. Had the thin layer correction been applied, do you think that would have moved those things to the right of the line?
Well, there's two parts. Number one, these kinds of points down there, I think you could get rid of those ones.
With the thin layer correction?
Yeah, I think so. And interface zones. I think the second thing is this is a little harder, but I think these ones up here, part of the problem is you'd really want some samples. I think one of the points we've always tried to emphasize is that the ability to infer soil type from a CPT signature alone has some uncertainty attached to it. And so I think the answer to some of these points, that upper part, it certainly looks like an upward finding sequence. If you had some boring samples, you could justify an adjustment different than the standard equations. So I think that would be where you'd have a chance to deal with those. And then the third thing is kind of, as I was saying, it's the same problems that I mentioned at the other sites. Computing the CSR and then computing the CRs, or the combination of the magnitude scaling factors for magnitude 9, I think they're conservative. So I think we'd see the CRRs would go up. And then the CSRs, the R sub D equations for earthquake-induced stress, for magnitude 9, they basically all get shoved up to RD's almost 1. And I think, as David was pointing out earlier, if you take a look at the nature of the records, I think that's too conservative. And what we'll see is we'd be able to bring the R sub D down. So that would bring the CSR down as well. So I think trying to sort that one out, it'd be a combination of changing the procedures as well as getting lab data and then looking at the thin layer corrections.
This mentions peak grounded acceleration.
Yeah.
No mention of, is it a single peak, or how long does this high acceleration?
Yeah, most of the records are comparable to these kinds of behaviors.
So
and that.
Just take the peak number?
Yeah, that's built into the procedure. So that's the whole idea of this is if you have a record like that, the PGA is based on, say, a peak value, but then the duration effects are accounted for by trying to add up the effects of all the different cycles.
Where is that into the acceleration? It says peak value.
Yeah.
It doesn't give you any time frame at all.
No. So one of the problems, if you're are you asking about how we do it in general, or are you asking about what we know at these particular CPT sites?
It seems to me that there needs to be some consideration of how long it lasts.
There is.
How long that acceleration lasts.
There is. So in the way we tackle duration effects is through what's called a magnitude scaling factor. The background behind it is that you go through a record, and every one of these cycles of loading, it's like a fatigue problem. So each cycle of loading contributes some amount of damage to the soil, and then what you do is you accumulate that damage. And because records have different durations, different waveforms, you try to take a large number of records to compute what would be kind of an equivalent uniform loading that would produce the same amount of damage, again, using more like fatigue models. And then when you do that, you can then correlate duration to things like the magnitude or the distance to the source, etc. You would see that Lou and John Stewart and colleagues, they came up with a magnitude scaling factor that accounted for distance, magnitude, and a few other factors. If you don't have that data, you end up correlating it back to magnitude alone. And so in essence, what we call our magnitude scaling factor is our accounting for duration of loading. Okay? Okay. Okay, one more, and then I'll get on.
Tokyo Bay,
Yeah.
yes, Popeye, this song. What you mentioned before earthquake or after the earthquake?
Oh, the SPTs?
No, the VS.
Oh, the VS. So there's a mix, but most of the shear wave velocities, all the ones that we were showing you were after. There are some data from before, certainly not as much. A lot of the majority of the SPT borings that I showed you in Tokamatsu study are from before, so they were for foundation design purposes. But they've been going back and then doing additional borings throughout the city to make sure that everything's consistent. As far as I understand, they have they're getting better data, but I don't think they've seen anything radically different than what they had from before.
That may have made a difference because after the earthquake, after the liquefaction, the soil might have settled or densified, and the VS would have come closer to the soil that we liquefied.
Yeah, that same argument is made when we look at SPTs or CPTs or any kind of penetration test data in a site that has liquefied before. There are certainly data that show that prior shaking does affect penetration resistances. Often with velocities, you can see examples of where they drop. If you have a really stiff site and you shake it with an earthquake, you can see the velocities drop after an earthquake because you've broken down cementation and aging. And you can see sites that were really loose, you can see them pick up. I don't think that would make the whole problem change. It's a good point, but I don't think it changes the main conclusion. So, in terms of repairs, starting in New Zealand, if you were trying to repair a home, you would only be doing this in categories 1 and 2 where the movements weren't very significant. And the options were pretty standard. The two photographs here are just underpinning techniques. This is underpinning where you get your jacks right underneath your perimeter beams and try to lift the foundation. This one over here is side pinning, where you have some kind of reaction plate or screw jack comes beside the footing and you put hooks underneath the perimeter beams and then you try to lift the foundation. The other two options are grouting. Over on the right is low mobility grouting. That's we would call compaction grouting. And or they were using resin grouting. And again, lifting things on the order of just inches. Anything larger than that, these weren't going to work. If you were going to be rebuilding and have a new foundation, then they also provided through the Department of Building and Housing guidance on what would be good practices or acceptable practices. And just threw this up to show you that these guidance documents are on the website. That in technical categories 1 and 2, again, settlements generally on the order of 4 inches or less. You get some pretty standard guidance. Technical category 3, it was different. And that's illustrated in these different sections out of their guidance manual. If you had less than, say, 4 inches of settlement or movement expected, like categories 1 and 2, the 3 recommended, or 3 of the 4 recommended options, look basically stiffening and strengthening the foundation to something more like the ones we showed you from Japan. Right? And you could do that with either a well-compacted mat that has geogrid reinforcement under it, and then you put your structural foundation on top, or you build a more substantial reinforced concrete, essentially a mat, and or you have thicker beams to really stiffen up the system. If you had technical category 3, the only guidance currently listed is to go to pile foundations, which is a great expense for any small structure. There are some trials that have been performed, and they're trying to develop guidance for trying to use deep soil mixing and other ground improvement methods in some way that gives a reasonable economy to the homeowners. But it is certainly a challenge and still ongoing. Japan, there's some very strong parallels to repair techniques. These are the same 2 kinds of underpinning techniques. On the left, getting into underneath the foundation and lifting it. Again, they have stronger foundations, so the lifting works quite well, and they can get into lifting things a greater amount. So anywhere they had larger settlements, they either did this form of underpinning on the left or side pinning over here on the right. And this just shows how they set up the jacks all the way along the perimeter of the building and then re-level it all at one time. And then you'd have to come in and grout underneath the slab under the mat to make sure you had good contact and whatnot. The other option which is common in Japan, is more of a re-leveling, using what they call point jack or spacing methods. In this case, you leave the reinforced concrete foundation where it is, and you instead lift and level the building above it. And so you lift it off its foundation, get it level, and then fill in structurally beneath it. This works quite well when the settlements were more modest, and it's quite a bit cheaper. The other two options were grouting techniques. Again, a compaction grouting technique on the left, a urethane grouting technique on the right. And those were the common ones. In terms of how this kind of played out, I got some statistics from a colleague, Dr. Abe from Tokyo Soil Research, as well as you can get information from the websites that are listed here. In the city of Urayasu alone, you're looking at about 9,500 homes, of which only about 900 weren't damaged. Then you have about 5,000 homes that were damaged in part with tilts less than about 1%. And then you have about 3,500 homes up here where you have tilts more than about 1%. So out of those homes, the different repair costs, underpinning was costing on the order of $75,000 to $125,000 for about a 600 square foot footprint. Okay, so not a very large area. If you were doing grouting, it was a little bit cheaper at $40,000 to $90,000. And then if you were able to use leveling techniques, then you're down to around $25,000 to $40,000 for the same 600 square foot footprint. Generally, it's not surprising, you only went with the underpinning when you had to. That was when the settlements were larger. The spacing construction techniques, being the cheapest, were used anytime you could when settlements were more modest and the foundations were all conducive to that. Urethane infusion was something that they discontinued fairly quickly because they were having problems with control. Inject it in one spot, comes up in the neighbor's lot, and that's not usually good. So that's the kind of techniques that are being used in Japan. Certainly quite a large cost for a homeowner, but a lot cheaper than rebuilding your home. Questions on the house repairs?
Releveling alone, would that fix the problem for the soil is liquefied? If you have an ongoing earthquake like Christchurch, which is still ongoing fix, and releveling by itself, it's not going to prevent the future similar damage, right?
It's a great point. So, the homeowners are kind of in a dilemma, right? So what you see is you can re-level. It might cost you $50,000, but you have not made your structure safe from going through it again. Now, at least they know the superstructure survives, so if they re-level it and they have another big earthquake, they'll have to re-level it again. So it's going to be a reoccurring cost, a risk that they're accepting. The cost of doing ground improvement under an individual home is much more prohibitive. So I'm not aware that anyone's really pursuing that as an option. So you're right, it doesn't fix the long-term problem.
And the piping they use, is that the screw pipes typical for these houses?
Oh, for the underpinning and the side pinning? So it varies depending on what the ground conditions are right near the foundation. Sometimes they'll use just reaction plates. Sometimes they have to do the screw anchors to get a sufficient reaction. Depends. Oh, I mean, even the soil liquefaction is only temporary, right? So as soon as the earthquakes pass and everything reconsolidates, you basically have a sandy soil. You can get good static reaction off it. Yeah. I'm not sure. It's not permanent. Remember, after they've jacked it up and re-leveled it, they're going to grout underneath the slabs for contact, so they're not permanently resting on those anchors. Yeah.
On the point jacking, that presumed that there was an intact mat slab in all those locations?
You mean where they're just lifting the house and then re-leveling it onto the mat? Yeah, they're presuming that they've still got good contact, but my understanding is it's pretty common that's part of the when a contractor's coming out or a firm's coming out to evaluate what's an appropriate way to lift the house, it's going to be dependent on what they think has happened, right? So if they think they've got some kind of not full contact all the way across the base, they're going to repair that as well. And so, I'm not sure that'd be reflected in those typical costs. Dave?
The photograph you showed with the minimal reinforcement
Yep.
foundation in Christchurch,
Still met the life safety objective of the building code, correct?
You could look at it that way. It does. I'm not sure the homeowners feel any consolation in that. I mean, that's true. Wood frame homes. One of my first introductions of this was the Loma Prieta earthquake, and the Moss Landing Marine Lab was a wood frame building. It was stretched. Footprint stretched about 4 or 5 feet. Building was badly racked, and all the occupants walked out. So, yeah, I think in terms of life safety, you can look at it in the positive view. Another positive view when you switching back to Japan, no fires, right? I mean, clearly the gas distribution systems have gotten better, shut-off valves and other types of things to eliminate any of those hazards. But the question is, when you still have thousands of homes which need repairs, where you have people dislodged, it really impacts the economy in a way that goes well beyond just the cost of leveling your house.
Just curious about the predictability on estimating settlements. We have a project that has some deep sands that are loose, and the recommendation is to use a grid of stone columns to create a more or less a raft over the liquefiable sands, and estimate of settlements are on the order of 2 inches. Is that something that you can actually predict in that situation? The approach you've described has been used by a number of people. Conceptually, it makes sense. It can offer you some economy. I think there is a lesson out of Christchurch, which is a great example to just give you some food for thought. This case history has been described by a number of people that involves a sports stadium there, where there was ground improvement. Stone columns were designed for the site to mitigate against liquefaction effects, protect the stadium and whatnot. My understanding is that there was a value engineering adjustment came in that proposed to not treat the entire thickness, but instead just treat an upper crust, that you'd be able to limit the settlements, you'd be able to protect life safety, and you'd save a lot of money. And so it seemed like a pretty logical idea. They did that. They saved a lot of money. Earthquake came along. Motions were a little larger than they were expecting, and now they're going to rebuild the stadium. And I think at that point you start to wonder if it was really worth it. I think a lot of these things, there's my personal opinion is you can take the numbers a little too literally. You can take them a little too literally in trying to optimize cost savings. You can say, I know this design earthquake loading, and if I take these numbers and sharpen the pencil, I can get to this 2 inches. But it's equally important to know whether you have a brittle system or not. It's very useful to take these kinds of analyses and repeat them for a range of hazards that are a little lower than you expect to a little higher than you're expecting. And if you get in a point where the settlements are going to start to take off on you with a little stronger shaking, I think you want to take that into your consideration. Yeah.
How about any instances where you might have like a deeper, the groundwater table is pretty deep, but you might have a perched groundwater table on top of the impermeable layer, and so you might not have liquefaction below that.
Okay.
But you might get liquefaction in the saturated sands above it. Any evidence of that? Or?
Yeah, there's some great examples of what you're describing were with some levee systems. Not just this earthquake. Actually, I'm thinking back to another one in Japan. I think it was around 2004, where levees were constructed on organic soils. The organic soils are very compressible, and so what happens is you get a lot of compression underneath the levee. What this leads to is the bottom part of the levee has settled substantially, a few feet, and then the bottom part of the levee is saturated. So even though the water tables, the rivers were low, the levee above the ground surface was largely dry. That part that had settled into this peat was still saturated. I'm not quite sure it's perched the way you're describing, but it kind of is analogous to it. And it was liquefaction of that lower part of the levee, which is attributed to some pretty dramatic movements in the levees. So clearly that kind of perching, if you've got the materials, could lead to some problems. I think what I should do is probably keep going, or I'll be right into the afternoon. But that kind of woke you up. Let's switch to utilities. Now, in terms of utilities, a number of lessons here. This is a picture of a large diameter water main. where it reinforces a lesson we've already seen many times, and it is the connections between the pipelines and any of the reaction blocks or other things where you can get concentrations of strain and damage. So attention to the details at the connections are very important. We saw a number of lessons with water treatment and sewer treatment plants being damaged in the Tohoku earthquake. This is just one of them. This water treatment plant, you can see the differential settlements all the way along the side of that tank structure. But more importantly, you can see settlements that are on the order of about 3 feet right along this linear feature here, and this is right over top of a pair of buried box culverts. The box culverts are connecting the different parts of the facility with all the plumbing and all the electrical to be able to operate the system. Those are the box culverts underneath the ground. There's 2 of them here. This one connects to that one, and at the connection you have about 1.5 feet of offset at the box culvert. This happens several places across the site, and sometimes those would open up and then the tunnel would infill with sands and everything eroding into the cavities. You can see that you've damaged all the electrical and the plumbing features, so that had to be repaired. All that had to be done before you could bring it back online. There are some great examples out in the distribution networks. This is very typical going across Uaresu, manholes floating out of the ground. You can see this one's quite dramatic. There's another one in the background, and this would go on and on and on across the city. Not often as dramatic, but you don't need to move much to tell you that you've broken everything off below the ground. And one of the things that was interesting about these is that you could often see that the movements were more pronounced right along the alignment of these different pipelines. Basically suggesting, and this is our understanding from our colleagues, that there was in different times fairly poor practices for backfilling the trenches. So you would dig the trenches, put the pipes in, and if they were backfilled with loose sands, the liquefaction would be even more dramatic right along these different utility lines. And so you had to be aware of that as well when you were trying to measure settlements by buildings, because that wasn't representative. You had to go out to the sides of the buildings and whatnot. But clearly lots of damage, floating of vaults and tanks, etc., disrupting the utilities. I showed you a slide earlier. Early estimates were about $500 million just to fix the roads and utilities in Uaresu alone. So huge hits. This is an example out in back out in the Tone River area near Kamisu. Sidewalk has been upraised by the flotation of a pipeline underneath it. You can also see all the water in the street. And I point that out because the crews are out on the street pressurizing the water lines, finding the leaks, and progressively working through the system. So there was a huge but overwhelming effort to try and get the water systems back on. I'm going to switch. There's a lot of more details that we hope to come out of Japan in the future. I wanted to switch to New Zealand because a lot of more detailed data are starting to come together there already. This is a map showing the water distribution network in Christchurch. This is next few slides of work by Misko Kubernovsky with Tom O'Rourke, working with, I think, John Bray, Russell Green, and a bunch of other people. If you zoom in, you have all the damage records for all the different utility systems. They have LiDAR records for being able to measure ground displacements. They have surface measurements of displacements. They've got it all into a pretty good GIS system, and then they can start to query it for lessons about how different materials have performed, etc. This is, again, one of those zoom-ins where the green zone is the area that's been mapped with LiDAR. They can then take all the performance of different piping materials and correlate it with ground strain and other measures of deformations. Punchlines that they've given are 2 here. I'm going to start down here at the bottom. The first is just the intuitive relearning the lesson that repair rates for all the pipeline types were about 10 or 30 times greater than the repair rates outside of liquefaction areas. So yeah, if you're in liquefaction areas, 10 to 30 times greater levels of damage and therefore repair rates than outside. That just reminds us that it's the ground deformations that are driving the damage to the pipeline systems. So that we knew. The other points to draw is that the stiffer, more brittle asbestos concrete and cast iron pipelines, they were showing repair rates that were about 4 or 5 times larger than what they had
with polyvinyl chloride or PVC pipelines, and those were in turn 2 or 4 times higher repair rates than what they had with the modified PVC pipelines. Again, perhaps intuitive, but it's data that illustrates that these plastic materials have greater ductility and can withstand ground movements without the damage you see with the more brittle systems. It's the kind of data that's hopefully very useful for us trying to convince more communities to move to more flexible piping materials. Certainly there can be a hesitancy from building officials to move away from something they've been using for a very long time. But these are certain motivating evidence when you have areas of ground movement. Now, a really great example comes out of Christchurch area. This is an area that was damaged in the first Darfield earthquake. A lot of damage to the piping materials. They went back in. They installed 2.6 kilometers of high-density polyethylene mains. Then they later had the Christchurch earthquake and then the June 2011 earthquake, and they got liquefaction in both those second events, ground movements up to 2 meters, and yet they had no reported damage to any of the HDP materials, even in the areas of lateral spreading. Now, if that's surprising, all you got to do is go to the Nice site at Cornell and look at some of the videos of their split box tests on HDPE pipes. Those pipes can take tremendous amount of strain and deformation and hold up together. So really good illustration of how these materials can behave well. The gas distribution network kind of reinforces the lesson. It's a liquid petroleum gas network. A good chunk of the network is in areas of liquefaction, and it comprised about 170 kilometers of pipelines. This network was all constructed with medium density polyethylene, and they used electrofusion welds, which performed well. Diameters were generally 2.5 to 12-inch diameters, and there was virtually no damage in all 3 events, despite being in areas of ground deformation. So again, these plastic materials work really well in areas of expected ground movements. Okay, so I'm going to switch to levees. Take a pause here. Any questions? Please.
I think you'd agree that we can make the red, yellow, green kinds of maps like were done following the event in Christchurch. We can make those pre-event for parts of San Francisco, for example.
Yes.
And we can identify areas where there are going to be large foundation problems.
Yes.
Given what you've learned from these events, is there mitigation, is there cost-effective mitigation that should be done on these houses in the marina, for example? 2 to 3 story, 100-year-old foundation.
Yeah, boy, if we could figure out a really cost-effective, good way to do it, we could probably make some decent money. I guess the question is what's cost-effective, right? I think certainly in terms of protecting the structure, making sure that you tie the foundation together. If you don't have a structure that's well tied together, anything you can do to stiffen and strengthen. You certainly can imagine different types of foundation modifications, that beams, grade beams, tying it together, etc. But the cost would not be small. And so there's really a question of what point would you be able to convince enough people that it's worth doing beforehand rather than accepting the risk after. And that really goes to just how well people are aware of the risk and perceive the risk, not just to themselves, but to their neighborhoods. I'm going to talk about this a little bit later, but one of the challenges as an individual homeowner, you might decide that for my own pocketbook, I'll take the chance that I will accept some damage in the earthquake and I'll deal with it then. But when you have a very pervasive problem like this, it won't be just your house, it'll be the neighbor's house and the other house and the other house and everybody's house. And then you have a much larger impact on the community, and when it's on the scale that you see in Christchurch, then that affects land value. If people leave the community, then you have everything from a drop in the local economy because you don't have people shopping, drops enrollments in schools, etc. So the damage to the community is much of an issue, and I think part of the issue then comes back to how do we deal with that in our decisions, and how we do building codes, land use planning, and those types of policies. I'm going to comment on that a little bit, and I think Lori's going to talk about it a lot later on. Any other questions? So for levees,
what I wanted to do is just give some examples of some of the different observations. The real lesson for the levees, I think, will take some time to get, and that is you have a levee system, and it's really about the resiliency and how fast you can recover the whole network of levees. And so there's going to be there's a couple studies underway to understand the management of the levee system, how to recover quickly, and go through the repairs. And that'll take a little while longer to milk. So I'm going to give you some of the quicker lessons. One of the things you found is you went up and down the different river systems, a lot of the liquefiable sediments along the river channels, meandering river channels, etc. What you got was fairly localized damage. So much of the levees, maybe 90% of the would be undamaged, and you would see these localized pockets of damage. And this is just illustrated here. Sometimes you would just see a sag over, what's that, maybe a 50, 100 meter long reach, and you get a sag of about a foot or so. Many times you could look at a Google map and you could see evidence that this would be in an old river meander, and all you've got is younger sediments in this particular section, and you can map the kind of details like that. Sometimes the damage was more extensive. In the front of the photograph you can see pretty bad cracking, movements maybe on the order of 2 or 3 feet. In the background is a section that was actually worse. It was essentially collapsed. It's already been reshaped and rebuilt as part of the recovery efforts. And then occasionally you would have these sections with more dramatic collapses. But again, over fairly limited reaches. So quite a range of movements, fairly localized, and this just reflects the natural geology and the scale of some of the river meander features, etc., that you could map to some of these damages. It just kind of keeps reiterating the importance of making sure you understand your geology. That contrasts with where you had levees along reclaimed lands, right? And reclaimed lands tend to be more uniform, and this is an example along Lake Hanuma. All along in that red circle is a levee system, and it's all on reclaimed lands, and along the entire length the levee is essentially pancaked. And the damage is very severe. It all needs to be rebuilt. This is kind of just perhaps an intuitive lesson, but certainly when we look in California and we have different parts of our levee systems where conditions are uniformly very poor and it's going to be much more difficult to recover versus areas where you're on more natural deposits and liquefaction hazards are more localized channels, and so it's a different recovery problem. And so those are types of things we want to make sure we understand. The Ministry of Land, Infrastructure and Transportation is responsible for levees in a number of these different prefectures. This is a summary of some of their data right after the earthquake, the number of cases from out-and-out collapse failures, different settlements, all the way through damage to revetments and gates. Generally, they had about 1,200 cases that they had to respond to, and the impressive part was just how fast they were on the emergency repairs. We were out there a month after the earthquake, and large portions of damaged areas were already being fixed. They clearly had in place the contractual means to get contractors out there. They had the materials ready, so they responded very quickly. When areas involved slumping of the levee and cracking and whatnot, often it just involved reforming the levee. When they had to reform the levee, they also came in and put down articulated concrete blocks as a slope protection against erosion. And in certain cases, they appeared to have judged that the damage, particularly we understand the cracking was so severe, they were worried about seepage erosion through cracks, so they wanted something a little bit more positive as a repair measure. And what you see is a levee that's been slumped, damaged, then reshaped, and then what they're doing is coming in the outside and putting in a sheet pile wall to be a more positive cutoff for seepage. This is an even more dramatic kind of example of this. In this place here, you can see the reshaped levee up here, putting a big berm alongside it, and then coming back in the berm and putting 2 rows of sheet piles, infilling between the sheet piles and basically forming a sheet pile levee wall to hold back waters in the upcoming flood season. So they got right on this, and by largely by the end of May, they had most of the levees repaired. So very impressive. Our understanding is that a lot of these repairs are considered preliminary, and then they come back later and do a more final repair to make sure that they think they can last over the long term. This is in fact a practice in the past. This is an example of a levee that was damaged in 2003, the Miyagi earthquake, and then it was repaired. And after they'd repaired it, they came back and did a final repair, and the final repair was to use mix-in-place deep soil mixing as a ground improvement. Now, the repaired section is shown up here in the background. There's no evidence of movements or cracking in the levee section in the repaired zone. Adjacent to it is an unimproved zone where you can see clearly some ground movement and some cracking. And what happens is if you kind of drill in at the contact between the treated and the untreated zone, you get a contrast in stiffness that leads to some problems. Now, the first thing is just pointing out that the ground improvement that they did in the treated zone, deep soil mixing, it was a block treatment. It produces a very stiff foundation, and then you reconstruct the levee on it. It doesn't deform much in the earthquake. Adjacent to it is untreated ground. The untreated ground is going to deform some amount. You get a difference in deformations, and what happens is that incompatibility of movements leads to transverse cracking across the levee. Transverse cracking is very bad because if you have a flood and the river comes up, then you can get seepage through the cracks, and that leads to erosion, and you can have seepage erosion failures through those cracks. Now, you can deal with that if you just recognize the problem, right, with filters and drains to prevent the continuation of any erosion, and or you've got to reconsider if you like that kind of strong contrast and stiffness between treated sections. But it's a good reminder of how those details would be very important when we're doing ground improvement. We see damage to levees as a result of scour throughout all the areas affected by the tsunami. I'm going to skip commenting on that just to save some time here. Up to almost my last one, this is to look at some features of dams. Now,
so I thought about the stiffness contrast, and if you were to repair the levee and then for whatever reason decided this is the end of the repair, maybe would some kind of tapering off of that improvement be preferred to suddenly stopping it?
That's kind of an intriguing question. I'm not really sure as you taper off a thinner, let's say a thinner soil cement section. I don't know how it would behave.
Like if you had them on 10-foot centers, maybe taper to 20 and 30 and 50 and then or something. I don't know.
I think I'd be worried in that case more with the idea that as you went to bigger spacings, at some point you're tracting more load onto the soil cement, and then you might get cracking on it anyway. I kind of what I'm drawn to when I look at this is just making sure you include filters and drains in the section. Because getting a transverse crack like that can be tolerated if in the levee section yourself you put in a filter and drain so that the crack heals itself. So I think that's what I'd be drawn to.
You mentioned they had contracts in place to allow them to do those internal repairs quickly.
Yep.
Do we have something like that in the
We do. I think there's issues of scale. So, for example, the Department of Water Resources has contracts in place. There are different efforts depending on different water districts and whatnot to make sure that you have materials stockpiled so that you have access to them. And certainly we see it in examples when we have our big rainstorms, our floods, right? You have the flood fighting teams out on the levees, and they've got the ability to execute contracts quickly. Right? So we have analogous things. Certainly is a question of whether they're adequate for when you get a very large event and then everything's the damage is very pervasive. Do we have the capabilities? Do we have enough contractors, enough materials, et cetera? So I think we can do better at preparedness. By and large, dams did quite well in the Tohoku earthquake. There are some good lessons about dams from the Chile earthquake, which are described in the special issue on the Mali earthquake in EERI Spectra. So I'd encourage you to go read that one. And this, I just wanted to stay in Japan. In general, dams performed very well. The inspections by the various agencies involved looked at over 400 dams. There was just a modest number of them which had some minor transverse cracking, mostly longitudinal cracking. Movements weren't very significant, nothing that would be a serious concern and couldn't be repaired. Performance was pretty good, shaking offing on the order of 0.2 or 0.4 G range, as David showed earlier. There was one dam that failed, and it is a non-jurisdictional dam. It's an irrigation dam, so it falls in their non-regulated category. It's about a 60-foot high dam, constructed in 1949 or completed in 49.
using not very good construction techniques. This is a aerial view of the dam. The main dam is down here on the bottom, and also there's an auxiliary dam that we'll look at as well. Again, about 60 feet high. The dam breached as a result of the earthquake. The breach went down the channel, destroyed about 5 homes, a little bit of the local infrastructure, and killed about 8 people. We have a lot of non-jurisdictional dams throughout the U.S. and a lot of old dams of this vintage. And a lot of our national dam safety programs or dam safety organizations in the states are overwhelmed. This really goes to making sure that these organizations are funded to be able to look at these kinds of examples that can be left unattended. So kind of zooming in, this is a photograph taken, I believe it's like 25 minutes or so after the earthquake. You can see that it's already breached. The eyewitness thought that they had noticed movement of the dam in the upstream direction first. This actually contradicts the analysis results. Everyone who takes a look at the analyses would predict, based on the slopes and assuming some homogeneity of the dam, that movements would be in the downstream direction. Resolving those details require better characterization data, which we don't have for the dam, especially now that it's breached and gone. This is the breach section. You can see in the background the reservoir floor and then the perimeter of the reservoir, the watermark all the way around it. Just looking through the breach section, you see an awful lot of this black material across the exposed abutments. That exposed material is a black organic silty clay. It's a fairly high plasticity material. You would see roots, tree stumps, and other things in the foundation. Basically, the foundation was not stripped or cleared in the way that you would expect in any kind of modern foundation. And those organic materials are obviously a concern for stability. Above it, you had a silty sand fill, this light brown fill, by all evidence not well compacted. In locations, you're looking at 5 to 10% fines, so not a lot of fines. It certainly is a material that one would expect to be prone to liquefaction. We have no SPT or CPT data in these materials. Hopefully some might be obtained in the remnants at some point, but not yet. You have the redder brown fill is a more clay sand, sandy clay, slightly plastic, more resistant to erosion. And then over top of it you have another lighter brown sandy silt material. What happens is when you look at this dam with its typical slopes, 2.5 to 1 or flatter on both sides, any reasonable assumptions of properties, you'd think the dam would perform maybe not great, but not poorly. The only way to explain the slumping and the breaching is to expect that there is some loss of strength as a result of the earthquake loading. Of course, the candidates are liquefaction in the lower loose fills or something along that organic foundation layer. But those are details that we hope to get in the future. Now, when you switch and look at the auxiliary dam, you also see a very large slide form in the upstream shell. That slide didn't damage the downstream slope, so it's limited itself to towards the reservoir side. There are 2 possible mechanisms to consider here. Now, the obvious one is that it's similar mechanism to the main dam, where you maybe have looser materials, silty sands, maybe you had some liquefaction or loss of strength in the embankment materials that led to the failure. The other possibility, though, is that it could be a rapid drawdown failure. What happens in the main dam breaches, you drop the reservoir so rapidly, you produce rapid drawdown all the way around the perimeter of the reservoir, and in fact all the way along the reservoir perimeter walls you would see these rapid drawdown slides in the covering materials. So again, this could be either of those mechanisms contributing to it. Okay, so any question on the Fujinuma Dam? Okay, well I'm going to wrap up and then we'll be right for lunch. Just a few concluding remarks. David had the best equation of the day. Data equals good. We completely agree with that equation. Having spent so much in time working with the Peer Center, I just always have to show this silly triple integral. It's a lot easier to understand if we just put it in boxes.
And just to walk through and think about what we're doing. We start with some idea of intensity measures, our understanding of the ground motions. We're going to move through some response model, whether it's predicting how we expect deformations to occur in our levees or in our dam, or deformations in our piping materials or foundations. So then that gives us some idea of the response of our system. We are then going to move and look at damage. Do we have cracking? Are we going to have to repair things, etc.? From those damage measures, we're going to be looking at losses. Those losses could be as simple as, are we going to have to repair the foundation, re-level the building? Or those losses could include things like, if I breach that dam and the reservoir release kills someone, what are my losses, both in terms of life and property? So those losses lead us to then trying to make some decision. And when we look at this equation, we often walk through this and we tend to think of it as an individual owner, an individual site, or an individual property. And I think the questions that increasingly we need to be thinking about in our profession is, whose losses are we concerned with? Is it our individual losses, or is it the losses of our community? And when we get to making a decision based on that, is that a decision that should be made solely by the individual, or at some point is it a community decision? And I say this, if you just think of, you own this one facility, this one plant, this one structure. If you go through the calculation of the liquefaction hazards, like we talked about the stone columns, you might conclude that, well, it's cheaper for me to accept the damage from liquefaction and then repair my structure after than it is for me to fix it ahead of time. The thing we have to think about is, what happens if it's not just my structure, but I'm in an area where this liquefaction hazard is very pervasive, and it's my structure, my neighbor's structure, and everybody else in my entire area's structure. And when all the structures are damaged, that has a different level of consequences. All of a sudden, you don't have a local economy. You have people who are going to move out. Your land prices drop. It can affect the ability of an entire city to recover. And your losses are no longer just, I get to fix my building. It could be years before you get your building fixed. Think of the closure of the central building district in Christchurch. You know, that broader loss to a community means that we need to rethink what happens in these rare events when all the damages are very strongly correlated. To kind of just re-emphasize that, I borrowed this slide from Laurie Johnson, who is going to reiterate a number of issues, I think in more detail, about how we approach this issue. And just to kind of tie it with what I was just talking about, we have our understanding of the engineering aspects of this, the research investigations, understanding of the physics and whatnot. We then have some understanding of our hazard, which periodically we update with some synthesis. So we have our understanding of how the hazard relates to our communities. And then you have a whole set of derivative products, which similarly are updated periodically, from building codes to infrastructure design, land use planning, response exercises, etc. And then you take all that and it goes into some idea of risk management. And when we're managing that risk, is it ours, or is it at the community level? So if we start thinking more about our communities and the recovery of our cities, we've got some questions we need to start spending more time on. And one is, are we really adequately considering what happens when we have these pervasive geotechnical hazards? So like the city of Richmond in Vancouver is on a great big delta, that the whole area is going to be affected. We have certainly more examples up and down the West Coast and elsewhere like this. Are we considering the complex interdependencies of our infrastructure and the community? So when you have disruptions to your utilities and your gas lines and levee systems and et cetera, how does that affect the community, the land prices, the economy, the insurance structure, all those types of things? We're not necessarily thinking yet in that level, although there certainly are efforts that way, as Laurie will describe later. And then lastly, the propagation of uncertainties or knowledge gaps across this. And this goes to discussions earlier about how well we can predict some things. Sometimes if we have something wrong where we think a certain soil will behave one way and we're wrong, we don't get it wrong once, we get it wrong everywhere, right? If it's our standard of practice. If we think we're predicting settlements right, but we're doing it wrong, we get it wrong everywhere. If we don't know there's a fault there, we get it wrong everywhere. And so sometimes our uncertainties are very strongly correlated, and when you get to a rare event, the consequences can be much more broader and severe than just thinking about individual property losses. And so I think we really need to think about how those all come together in making decisions. In some sense, this really leads you to, in a risk analysis framework, you got to drive, you're going to make the system more resilient. There's different ways of saying this, but it's about having a certain amount of robustness in the system to withstand the uncertainty in our understanding of loads and behaviors. So, in concluding, I kept this short because I've already said everything I wanted to. In terms of pervasive hazards, just a reminder that these were known and they were identifiable from geological and historical records, as are the hazards that affect many of our other communities. These two earthquakes, I think, are going to be very seminal for our field, in large part because of the quality and the quantity of the data that we're getting is really unprecedented. The strong ground motion records mean that we know the loading so much better than we have in other case histories that we're much more constrained in what we're going to learn from it. What this translates to is a lot of opportunities for us to further advance performance-based engineering methods, because you're no longer comparing your design method against 1 or 2 or 3 case histories, you're doing it against dozens of them. And when you do that, you get a chance to quantify systematic bias in our engineering methods and to appreciate the dispersion in our methods so that we have a better appreciation for how accurate or inaccurate some of our design methods are. This applies to liquefaction, levees, foundations, lifelines. So again, I think this is going to take several years for us to digest everything that's coming out of these two earthquakes. In terms of risk, just reiterating that last couple slides I went through, it's just that we really need to make sure that we're thinking from a community perspective about the interdependencies of the infrastructure systems and how it affects the resiliency of our communities to respond and recover. We need to really work on public awareness. We always talk about that, but the public hears it. Sometimes they get numb to it, and there's a challenge to make sure they understand what it means to them, what these hazards can result in. And we need to rethink these geotechnical hazards from a community perspective when we are setting our building codes, our land use planning, and other activities, and policies. So I think listen very carefully to what Lori says later. I've heard it 3 times. I'm going to enjoy it yet again. So I do want to point you at the Gear Association website. A lot of the reports and data that I've described, especially the CPT and SASW data, will be up there, we hope before Christmas. We're just kind of cleaning up documentation on it. So it's a good resource. I also need to point out that a lot of what I was showing you is supported by the National Science Foundation through Reconnaissance Rapid Awards to a number of individuals going to both of these events. That there were numerous colleagues whose slides and information I am very grateful for, included throughout this. So hopefully you saw all the footnotes on the slides, contributions from many people. This really is a group effort, learning from these earthquakes. And EERI is a great organization for bringing people together to do that. And with that, I believe we're ready for lunch.